You are sitting in a familiar space, the walls of your room holding nothing more threatening than your furniture and the faint hum of electricity. Your body occupies a continuous region of space, your mind tracking the passage of time in a linear fashion. You assume that the universe beyond your window and beyond your comprehension obeys a consistency you can rely on. Cause produces effect. Objects exist where you see them, and space stretches evenly in every direction. Yet, the universe measured by science rarely conforms to intuition. In every observation, there are contradictions that refuse to reconcile. There are situations in which a structure exists that should not, regions where measurement obeys local logic but violates global rules, and phenomena that appear inert yet produce undeniable effects. These are not thought experiments or theoretical musings. They are the consequences of data, the unavoidable results of measurements and calculations that have been repeatedly verified. As you watch this video, you will encounter 20 paradoxes embedded in the fabric of reality itself. Each one is a contradiction between expectation and observation, a fracture in the assumptions that govern your understanding of existence. Nothing here is speculative fiction. Each paradox is rooted in the precise, inescapable evidence collected by decades of scientific inquiry. The question that guides our exploration is simple and unnerving. What does it mean when the universe consistently refuses to align with the rules it appears to have set for itself? The arrow of time and its reversal. You perceive time as flowing in one direction, from past to future, and you rely on entropy to mark this passage. Yet, at a fundamental level, the laws governing particles and fields are symmetric in time. Every interaction that produces irreversibility on a macroscopic scale could, theoretically, run backward. Observations confirm the unidirectional arrow, yet the microscopic rules allow no preferred orientation. This conflict between measurement and symmetry unsettles the foundation of causality itself. Consider a simple cup of water spilling onto a table. You watch as the liquid spreads, as droplets scatter, and as energy disperses into the surrounding air. In this everyday event, entropy increases. The pattern moves from order to disorder, and the process appears irreversible. The molecules themselves follow deterministic rules, obeying the forces of electromagnetism and quantum mechanics. Yet collectively, they create a directionality in time that you feel intuitively. The statistical behavior of trillions of particles gives rise to this arrow. Each collision, each transfer of energy, contributes to an irreversible cascade. Yet the microscopic equations that govern these interactions would produce the same outcomes if time were reversed. At the level of individual particles, nothing compels motion in a particular temporal direction. The paradox deepens when you consider that all fundamental interactions, electromagnetic, strong, and weak nuclear forces, do not distinguish past from future in their formal expressions. A particle collision observed in a lab produces identical trajectories, whether the clock moves forward or backward. Your observations, however, never witness an ice cube spontaneously reassembling from melted water, nor smoke retreating back into a fireplace. The unidirectional flow emerges only statistically, as an aggregate property. Measurement confirms a consistent temporal progression, but the underlying mathematics permits perfect reversibility. Entropy is the bridge between these scales. It quantifies the number of microscopic configurations that correspond to a macroscopic state. High entropy states are overwhelmingly more probable than low entropy states. In this sense, time appears to flow in the direction that increases probability. Yet, probability is not causation. No law demands that the cup spill, only that the odds overwhelmingly favor it. When you observe the arrow of time, you are witnessing the cumulative behavior of probabilities manifested across countless particles. Each measurement aligns with your expectation, but the expectation itself is an emergent property, not a fundamental rule. Observational cosmology introduces further complications. The universe itself began in a state of extraordinarily low entropy. The cosmic microwave background, relic radiation from the early universe, reveals a smooth, uniform distribution of energy, far more ordered than would be typical. From this initial state, entropy has increased continuously, establishing a cosmic arrow of time that mirrors your own local experience. The paradox is that the initial conditions required for this temporal asymmetry remain unexplained. You measure the flow of time, yet the source of its direction lies outside your ability to observe directly. Time, reversal, symmetry in microscopic laws also implies that for every sequence you witness, there exists a mathematically valid, temporally inverted sequence. In principle, a universe could unfold in the opposite direction, where entropy decreases, memories form before events, and effects precede causes. Such a universe is consistent with the equations, yet incompatible with every observation you can make in your own. The conflict between what is permitted by measurement and what is experience produces a subtle unease. You are anchored in time, observing irreversibility, while the underlying reality allows none. Ultimately, the arrow of time is a paradox of scale and perception. The deterministic, reversible world of particles generates a probabilistic, irreversible world of experience. Measurement confirms directionality. Yet the microscopic symmetry offers no explanation for why that direction is preferred. Causality feels fixed, yet its foundation is statistical, not absolute. Each second you perceive as flowing carries with it the silent tension, a lawless microcosm beneath, a universe indifferent to the passage of time, even as you navigate it as if it were fixed. The twin paradox of relativity. You assume that clocks tick uniformly, and that elapsed time is universal. Yet special relativity demonstrates that two observers moving relative to each other will age differently. This is not a calculation, but an experimentally verified reality. Fast-moving atomic clocks accumulate time at a measurably slower rate. The contradiction emerges between your intuition of shared temporal flow and the empirical measurements of moving systems. Imagine two identical clocks, perfectly calibrated, separated by vast distances and velocities. One remains stationary on the surface of Earth. The other embarks on a journey at a substantial fraction of the speed of light. When the traveling clock returns, it shows less elapsed time than its stationary twin. This is not conjecture. It has been confirmed repeatedly in laboratories and with satellites orbiting the Earth. Your everyday experience gives no hint of this effect. Time appears uniform and absolute, yet when measured precisely, it is not. The universe treats moving observers differently, and your assumption of shared temporal flow is revealed as an approximation valid only for low velocities. At the heart of this paradox is the relativity of simultaneity. Events that appear simultaneous to you may occur in a different order for someone moving at a different velocity. Observation confirms that time is not a universal backdrop, but a dimension intertwined with space itself. Your concept of now is not a shared property across the cosmos. It is a local perception, anchored to your frame of reference. The traveling twin's now differs from yours in a precise, measurable way. The sequence of events, once assumed fixed, depends entirely on motion. This divergence is not subtle. Atomic clocks flown on high-speed jets or satellites experience measurable time dilation. GPS satellites, for example, must account for both special and general relativistic effects to maintain positional accuracy. The system relies on the precise prediction that moving clocks will lag relative to earthbound clocks. This adjustment is not an interpretation. It is a requirement imposed by observation. Your perception of uniform time is incompatible with the empirical behavior of moving systems. Yet these deviations are embedded in the technology that governs your daily life. The twin paradox also highlights an unsettling feature of causality. You expect cause to precede effect in all circumstances. In the traveling twin's frame, some events in your past may appear to occur after events in their own past. Time dilation does not permit causal violations, but it forces a reconsideration of simultaneity and temporal ordering. Measurement confirms that your assumptions about the sequence of events, so fundamental to reasoning and memory, are local, not global. The universe does not privilege a single universal temporal sequence. The deeper unease emerges when you extend the thought experiment to extreme velocities. As motion approaches the speed of light, time dilation becomes dramatic. Minutes for the traveler may correspond to years for the stationary observer. Your intuitive understanding of continuity, of shared experience across space, collapses. Observation reveals that each frame of reference contains its own temporal reality. Aging, duration, and the perception of change are not absolute. They are conditional on motion. This phenomenon is not limited to theoretical constructs. Experiments with particles moving near light speed in accelerators demonstrate the same effect. Muons, created in the upper atmosphere, survive longer than classical predictions because their internal clocks run slower relative to Earth. Observation confirms that motion directly alters temporal experience. Time is not a single river flowing identically for all observers. It is a flexible, frame-dependent quantity, measurable and undeniable, yet fundamentally at odds with intuition. Ultimately, the twin paradox forces you to reconsider the meaning of simultaneity, duration, and age. Time is not a universal metric that binds all observers together. Measurement confirms divergence. Experience suggests uniformity. The conflict between perception and observation persists, a quiet tension that underlies every journey through space and every measurement of moving clocks. In your own life, time feels continuous and shared. Yet reality, as quantified by experiment, is far stranger. Each second is experienced differently depending on motion, a paradox encoded into the fabric of space-time itself. Wave-particle duality. Light appears continuous, smooth, and predictable. Yet when measured at the quantum level, it behaves like discrete particles. The double-slit experiment confirms this. A single photon produces an interference pattern only when not observed, but collapses to a point when measured. You are confronted with a reality where existence is conditional, where observation defines state. Consider the simplicity of sunlight streaming through a window. To the unaided eye, the rays are uniform, blending into a continuous illumination that fills the room. Classical physics treats light as a wave, a propagating disturbance in an electromagnetic field, carrying energy smoothly across space. Your intuition aligns with this view. Light travels in a predictable, continuous fashion, and photons are merely convenient abstractions. Observation confirms a pattern consistent with continuity. Yet the microscopic reality is far less straightforward. When photons are emitted individually toward a barrier with two slits, the expected particle behavior does not emerge. Each photon seems to interfere with itself, forming a pattern characteristic of waves. No single particle should produce such an effect. Measurement reveals that the photon does not occupy a single path in the conventional sense. Instead, it exists as a probability distribution, a spread of potential outcomes that is only resolved when forced into a definite state by observation. The act of measurement itself imposes reality. When detectors are placed to determine through which slit a photon passes, the interference pattern disappears. The photon behaves as a particle, a discrete entity occupying a single location. Observation collapses the probability distribution into a singular outcome. What you measure is no longer an abstract wave, but a localized particle. Reality, in this sense, is contingent. It is defined not by the intrinsic properties of the photon, but by the act of observation. This phenomenon is not limited to photons. Electrons, neutrons, and even larger molecules display the same duality when passed through analogous experiments. The interference patterns emerge only in the absence of direct measurement. The principle is experimentally confirmed, repeated across decades, yet it defies intuition. A single particle produces effects as if it were simultaneously everywhere it could be, and only chooses a definite position when observed. The universe does not adhere to classical determinism at these scales. Wave-particle duality challenges the very notion of existence independent of perception. You assume that objects have positions, velocities, and properties, whether you look or not. The experiments demonstrate otherwise. At the quantum level, states are potential until measured. Measurement does not merely reveal pre-existing properties, it defines them. The dichotomy between smooth waves and discrete particles is not resolved by deeper observation. It persists as a fundamental feature of reality, confirmed repeatedly by experimental data. The double-slit experiment also reveals a temporal tension. The photon appears to know whether it will be observed, influencing its behavior in a manner consistent with the experimental setup. Observation retroactively defines the outcome of events that have already unfolded in space, a disquieting implication that challenges linear cause and effect. The sequence of interactions is measurable and reproducible, yet it produces results that resist a conventional, classical narrative. Ultimately, wave-particle duality forces you to reconsider what it means for something to exist. Light and matter are not simply objects with fixed intrinsic properties. Their behavior is conditional, intertwined with observation and measurement. The universe at its most fundamental level is neither fully continuous nor fully discrete. It is a structure in which probability and potentiality govern reality until interaction enforces certainty. You move through a world of stable perception, yet underlying that stability is a quantum landscape in which existence is provisional, defined by the act of measurement itself. Schrödinger's boundaries. The quantum world suggests that particles can exist in multiple states simultaneously, yet macroscopic objects do not visibly share this ambiguity. The paradox emerges from the continuity between micro and macro. The boundary between observable certainties and probabilistic states remains unexplained, despite measurements confirming both realms. At the smallest scales, particles are described by wave functions, mathematical entities that encode all possible states a particle can occupy. The equations are precise, predictive, and experimentally verified. An electron does not possess a single position or velocity. It exists as a distribution of probabilities. Measurement forces the wave function to collapse, selecting one state among many potential outcomes. Observation converts potentiality into reality. Yet before that act, no definitive state can be assigned. This behavior is strange, but in the microscopic world, it is routine. Photons interfere with themselves, electrons tunnel through barriers, and atoms occupy superpositions of energy levels. Measurement confirms these predictions with extraordinary precision. The rules are consistent, reproducible, and deeply counterintuitive. The universe at the quantum scale does not behave like the continuous, deterministic world of classical physics. The paradox intensifies when these principles are applied to larger systems. Schrödinger's thought experiment, with its cat enclosed in a box, illustrates the tension. The cat, considered as a quantum system entangled with a radioactive particle, exists in a superposition of alive and dead, until the box is opened and an observation is made. At the microscopic level, superpositions are expected and measured. Yet, at the scale of everyday objects, you never observe such ambiguity. A cat is never partially alive or partially dead in your perception. Measurement collapses states so effectively in macroscopic systems that the superposition seems inaccessible, even though the underlying principles remain identical. The boundary between micro and macro is neither sharp nor formally defined. Decoherence provides a partial explanation. Interactions with the environment rapidly entangle and disperse quantum information, effectively masking superpositions at larger scales. Experiments confirm that decoherence occurs predictably, yet it does not eliminate the fundamental probabilistic nature of reality. It merely renders it unobservable for complex systems. You experience certainty, but that certainty is emergent, contingent on environmental interaction, and not an intrinsic feature of the universe. The unsettling implication is that the world you inhabit, tables, chairs, even your own body, exists in a state of apparent definiteness only because of interactions you cannot perceive. Measurement, at some level, governs the transition from potentiality to actuality. The classical stability you rely upon emerges from a substrate of probabilities. Your perception and the macroscopic objects around you are the cumulative effect of countless quantum events collapsing in patterns too complex to observe directly. Observation is not merely a passive act. It is a force shaping the manifestation of reality. Experimental evidence supports this continuity. Superpositions have been observed in molecules composed of thousands of atoms, and quantum interference patterns have been measured in systems approaching the macroscopic scale. The principle does not fail. The observable ambiguity simply becomes harder to detect. The universe does not draw a strict line between quantum and classical. The boundary is practical, not fundamental. Measurement defines where you experience certainty, not where the rules of physics change. Ultimately, Schrödinger's boundaries confront you with the fragility of apparent certainty. Your world feels stable, defined, and consistent, yet the underlying substrate is probabilistic, contingent, and fundamentally ambiguous. The separation between micro and macro is not a law of nature, but a feature of perception and interaction. Measurement resolves ambiguity in a manner that is local, not absolute. The paradox lies in the continuity. The principles that govern the smallest constituents of matter extend throughout the universe, yet your experience is confined to the emergent patterns of stability, masking the underlying indeterminacy that permeates all reality. The information paradox of black holes. Matter. Falling into a black hole seems to disappear, yet quantum mechanics dictates that information cannot be destroyed. Observations of Hawking radiation imply that black holes slowly evaporate. But if information escapes, it does so in a form that appears scrambled beyond recognition. Reality presents a system where measured phenomena violate intuitive expectations of conservation. Imagine an object crossing the event horizon, the invisible boundary surrounding a black hole. From your perspective outside, the object appears to slow, asymptotically approaching the horizon, without ever fully passing through. Time itself is distorted by the black hole's gravitational field. Observations confirm this effect repeatedly. Light emitted from the object is redshifted, stretched, and dimmed, as though the universe itself is dilating in its vicinity. The object's matter and the information encoded in its structure seem to vanish from observable reality. Classical general relativity treats this disappearance as absolute. Anything crossing the horizon is causally disconnected from the outside universe. No signal, no light, no matter can escape. Measurement beyond the horizon is impossible. Yet quantum mechanics imposes a different constraint. Information, the complete description of a system's state, cannot be destroyed. Experiments and theoretical frameworks confirm this principle, making the total annihilation of information fundamentally incompatible with physical law. The contradiction emerges starkly. Black holes, as observed, erase the very information that quantum theory insists must be preserved. Hawking radiation offers a partial resolution, though one that deepens the unease. Quantum fluctuations near the event horizon produce particle-antiparticle pairs, some of which escape, carrying energy away from the black hole. The black hole loses mass gradually, shrinking over vast timescales. Observation confirms the emission spectrum predicted by theory. Yet the radiation appears thermal, random, and uncorrelated with the matter that initially fell in. If information is preserved, it is encoded in a form so scrambled that reconstructing it seems impossible. The object that entered the black hole cannot be recovered, its identity dispersed across a subtle, inscrutable quantum imprint. The implications are profound. You are accustomed to the principle of conservation. Matter and energy persist. Information is retained. A system exists. Its state evolves predictably, and records of events can, in principle, be traced. Black holes defy this expectation. Measurement confirms both the disappearance of matter and the persistence of physical law. Information cannot vanish, yet the universe offers no straightforward mechanism to retrieve it. Reality is consistent with measurement, but inconsistent with intuition. The paradox also extends to the horizon itself. The so-called firewall hypothesis suggests that quantum effects may produce high-energy phenomena at the event horizon, disrupting smooth space-time. Observations are indirect, but the predictions are precise. The horizon, once assumed passive, may be active in ways that directly influence infalling matter. Measurement of gravitational waves and black hole mergers hints at these subtle interactions, though the exact nature of the horizon remains unresolvable. The boundary is no longer merely a point of no return. It is a locus where fundamental principles collide, where causality, quantum mechanics, and general relativity intersect in ways that strain understanding. Ultimately, the information paradox forces you to confront the tension between what is measurable and what is comprehensible. Black holes exist. Their behavior is consistent with observation. Information cannot be destroyed. Quantum theory is confirmed experimentally. Yet the mechanism connecting these facts remains elusive. Matter disappears, the universe evolves, and laws hold, while simultaneously presenting a scenario in which intuition about conservation fails. The paradox is not a gap in imagination or theory. It is embedded in the measurements themselves, a quiet tension encoded in the very structure of space-time and quantum reality. Dark matter's invisible influence. Galaxies rotate in a manner that suggests the presence of massive, unseen structures. Observations indicate that 85% of matter in the universe exerts gravitational effects without interacting with light or detectable forces. You see the motion and structure, but the source remains invisible. Measurement confirms presence without visibility. Consider the spiral of a galaxy. Stars orbit the center at velocities that, according to the visible mass alone, should fling them outward. Classical physics predicts a decline in rotational speed with distance from the core, yet observation demonstrates near constant velocities across vast distances. The discrepancy is measurable, precise, and confirmed across thousands of galaxies. You perceive the motion, the shape, and the density of luminous matter, yet these alone cannot account for the gravitational forces observed. Something unseen holds the system together. This unseen influence is what we call dark matter. Its existence is not inferred from speculation, but from repeated, consistent observation. Galaxy rotation curves, gravitational lensing of light from distant sources, and the cosmic microwave background all indicate a pervasive gravitational field that cannot be accounted for by ordinary matter. Measurement confirms mass and gravitational pull without revealing a corresponding electromagnetic signature. The source is physically real, yet invisible. It interacts with the universe through gravity alone, eluding every direct method of detection. The paradox emerges from your expectation of correspondence. In ordinary experience, mass is observable. You can see, touch, or measure the objects responsible for gravitational forces. Here, the universe violates that intuition. Stars orbit an invisible hand. Galaxies form and cohere not by the matter you perceive, but by something fundamentally hidden. You are confronted with a reality in which the dominant component of the cosmos cannot be seen, and yet its presence is unavoidable. Observational cosmology extends the scale of this influence. Clusters of galaxies are bound together by more than visible mass. Light from distant galaxies is bent in precise patterns that map the distribution of gravitational potential. The resulting lensing shows concentrations of mass where no visible matter exists. The pattern of mass inferred from these measurements aligns with predictions of dark matter's behavior, yet the particles themselves remain undetectable. Measurement reveals the effect, but conceals the agent. The implications extend further. Dark matter does not emit or absorb light, nor does it interact through known forces beyond gravity. It shapes the evolution of the universe from its earliest moments, guiding the formation of galaxies and the large-scale structure of the cosmos. You see the results: clusters, filaments, voids, but the architecture is invisible in its origin. Reality is structured by something unobservable, a scaffold that is inferred with certainty, yet inaccessible to direct experience. Experimental efforts continue to probe the nature of dark matter. Detectors deep underground, designed to isolate rare particle interactions, have found no confirmed events. Collider experiments have yet to produce candidates. The absence of detection reinforces the paradox. Observation and theory demand its existence, yet direct measurement provides no further clarity. The universe enforces a presence that defies your ability to perceive it directly. Ultimately, dark matter exposes the fragility of assumptions about what is real. You navigate a cosmos in which the majority of mass remains invisible, where motion and structure are governed by forces whose sources cannot be seen. Measurement confirms influence without visibility, interaction without comprehension. The universe is partially hidden in plain sight. You can quantify its effects, map its distribution, and predict its influence, yet the substance itself remains elusive. Reality, as observed, is inseparable from what cannot be observed. The dominant component of existence is silent, invisible, and undeniable. Dark energy and accelerating expansion. The universe is not merely growing, it is expanding at an accelerating rate. Observations of distant supernovae reveal this trend, yet the mechanism driving it remains unknown. The cosmos stretches in defiance of gravity, creating a persistent tension between measurement and theoretical understanding. When you look at the night sky, you assume that the distances between galaxies are relatively stable over human timescales. You may imagine the universe as static, with stars and clusters moving slowly under mutual gravitational attraction. Yet precise measurements reveal something fundamentally different. Light from distant Type Ia supernovae arrives fainter than expected, indicating that these galaxies are receding faster than classical models predict. The expansion is not uniform or constant. It is accelerating. This is not an inference or a hypothesis. It is a directly measured, reproducible observation. The agent responsible for this acceleration is called dark energy. Its nature is unknown, yet its effect is undeniable. Observations of the cosmic microwave background, large-scale structure, and baryon acoustic oscillations all converge on the same conclusion. A pervasive, repulsive influence is counteracting gravity, pushing galaxies apart at an increasing rate. Measurement confirms the presence of an effect, but not its substance. You perceive the results, but the cause remains hidden, inscrutable, and fundamental to the evolution of the cosmos. The implications extend beyond the expansion of space. Gravity, the force that binds matter into planets, stars, and galaxies, is being counterbalanced on the largest scales by a phenomenon for which no conventional mechanism exists. The universe grows not only in size, but in the pace of growth itself. The acceleration is subtle locally, imperceptible in daily life, yet when aggregated across billions of light years, it dominates cosmic evolution. You observe the structure of the universe as stable, yet underlying this appearance is a force subtly, inexorably stretching space itself. The theoretical tension is profound. Einstein's equations permit a cosmological constant, a uniform energy density permeating space, but the measured value of dark energy is staggeringly small compared with estimates from quantum field theory. The discrepancy spans dozens of orders of magnitude. Measurement is precise and consistent, yet our models fail to reconcile the observed effect with expected values. Reality demonstrates acceleration. Theory cannot explain why the magnitude is what it is. The universe stretches, and our understanding lags, leaving a persistent, measurable contradiction. Dark energy also redefines your perception of distance and causality. Galaxies receding from one another do not simply move through space. Space itself expands between them. There is no force in the classical sense, no local acceleration of matter against inertia. Observation shows that the fabric of space-time itself is stretching, altering distances without applying a conventional push or pull. This distinction is measurable. Redshifts encode the expansion, and yet the mechanism is inaccessible to direct experimentation. You can quantify the rate, but you cannot grasp the origin. The accelerating expansion has long-term consequences that are equally measurable and deeply unsettling. Over cosmic timescales, regions of the universe will recede beyond observable horizons, severing causal contact. Light from distant galaxies will eventually fail to reach you, leaving the cosmos increasingly empty from your observational frame. Measurement predicts isolation, a universe in which the expansion driven by dark energy dominates the observable landscape. The structures you see now are temporary. The universe is dynamic in a way that outpaces intuition. Ultimately, dark energy challenges every assumption about balance, causality, and the forces that govern existence. The cosmos behaves as a measurable system in which repulsion dominates over attraction, yet the origin and mechanism of this repulsion remain unknown. Observation confirms acceleration. Theory struggles to explain it. And perception remains rooted in classical intuition that no longer applies. You witness expansion, acceleration, and inevitability simultaneously. Reality is stretching, measurable and undeniable, while its cause remains entirely beyond comprehension. The Fermi paradox. The galaxy contains billions of stars with potentially habitable planets. Statistically, intelligent life should be widespread. Yet the night sky is silent. Observation and expectation diverge, producing a paradox where the absence of evidence becomes evidence of a strange, unseen principle at work. Consider the scale of the Milky Way alone. It contains hundreds of billions of stars, many accompanied by planets within their habitable zones. Exoplanet surveys confirm that Earth-sized worlds are common. If life emerges readily under suitable conditions, and if intelligence is a natural consequence of evolution, the galaxy should be populated with civilizations, each occupying its own niche in space and time. Yet the silence persists. No signals, no observable artifacts, no unmistakable signs of technological activity reach you. Measurement shows a void where abundance is statistically predicted. The paradox is not merely a matter of probability. Technological civilizations, once established, have the potential to expand rapidly across stellar distances. Even modest colonization rates, projected over millions of years, should fill significant portions of the galaxy. Observation, however, reveals no evidence of such expansion. The night sky presents only stars, nebulae, and the gravitational scaffolding of visible matter. The predictions of statistical models conflict with the reality you can measure. The discrepancy is precise, reproducible, and persistent. Several explanations have been proposed, each grounded in observational or theoretical constraints, yet none fully resolve the paradox. Perhaps life is rare, constrained by factors you have not yet quantified. Perhaps technological civilizations self-destruct before spreading widely. Perhaps advanced civilizations deliberately remain undetectable. All of these possibilities are consistent with measurement and with known physics, but each implies a universe profoundly different from your intuition. The absence of observable activity is itself a measurable phenomenon, yet it resists the expectations derived from statistical reasoning. The paradox also challenges assumptions about time and scale. The galaxy is billions of years old. Even a brief window of 1,000,000 years is sufficient, in principle, for detectable activity to occur. Observations indicate no such activity during your observational epoch. The statistical probability of civilizations emerging is high, yet the evidence is absent. The divergence between temporal expectation and empirical observation becomes a constraint on the universe itself. The silence is real, measurable, and unambiguous, yet it defies your assumptions about what is likely. Gravitational measurements, searches for technosignatures, and detailed surveys of nearby stellar systems have refined the scope of the paradox. Observation confirms the presence of numerous potentially habitable planets, yet no artificial structures or emissions are detected. The universe appears systematically quiet in a manner that is inconsistent with models of widespread intelligence. Measurement indicates that life may exist rarely, transiently, or in forms inaccessible to your instruments. The contradiction between expectation and observation persists, precise and undeniable. The Fermi paradox is unsettling because it exposes the limitations of inference based solely on probability. You assume that given opportunity, intelligent life should arise and expand. Yet the empirical universe contradicts this, forcing a reconsideration of the assumptions underlying your predictions. Silence is measurable. Absence is verifiable. The paradox emerges from the tension between what you can calculate and what you can observe. Ultimately, the Fermi paradox confronts you with an uncomfortable implication. The galaxy is vast, old, and filled with potential, yet the absence of detectable civilizations is a constraint on reality itself. Observation confirms the abundance of stars and planets, yet the expected abundance of intelligent life is conspicuously missing. You witness an observable universe that is simultaneously rich in opportunity and empty of the expected activity. Measurement defines the silence, and in that silence, a profound and unresolved tension persists, shaping your understanding of life, probability, and the cosmos itself. Quantum entanglement. Two particles separated by vast distances exhibit correlations that defy classical causality. Measurement of one instantaneously affects the other, confirmed repeatedly in laboratory experiments. The paradox is not merely conceptual. It challenges the locality of influence, collapsing assumptions about separateness in space. Imagine a pair of electrons generated together in a laboratory and then moved apart by kilometers or more. Each electron possesses a property, such as spin, that can be measured along a chosen axis. When one electron is measured, its spin assumes a definite value. At the same instant, the distant electron's spin aligns perfectly with the first, in a manner predicted precisely by quantum mechanics. Measurement confirms the correlation. No signal travels between the particles at light speed or below. Yet the outcome is consistent, instantaneous, and reproducible. The universe appears to enforce a connection across space that classical physics cannot accommodate. This behavior was famously formalized by John Bell, who demonstrated that no local hidden variable theory could account for the correlations observed in entangled particles. Laboratory experiments have repeatedly confirmed violations of Bell's inequalities. Observation leaves no ambiguity. The particles behave as a single system, regardless of the distance separating them. Classical assumptions of separateness, locality, and independent existence of distant objects are incompatible with measurement. You experience objects as discrete and independent, yet reality, as measured, is fundamentally relational. The paradox extends beyond laboratory setups. In principle, entanglement can span astronomical distances. Photons from distant stars or quasars could be entangled, and yet the correlations would persist, observable in principle. The universe itself becomes a network of potential connections that are instantaneous, non-local, and constrained by probability rather than spatial separation. Observation confirms these correlations in controlled conditions. Their implications suggest that space, as you perceive it, does not fully define the limits of influence. Quantum entanglement also forces reconsideration of causality. Classical reasoning assumes that events are sequential, with causes preceding effects within light cones. Measurement of an entangled particle does not transmit usable information faster than light, yet it establishes correlations that are instantaneous and globally constrained. Observation confirms that the classical structure of cause and effect is insufficient to describe the fundamental relationships between distant particles. The world behaves as if the separation between points in space is, in some respects, irrelevant. The unsettling element lies in the universality of the effect. Entanglement is not a peculiarity of exotic particles or extreme conditions. It is a property of the underlying quantum state of matter. You move through a world in which the behavior of tiny constituents obeys rules that disregard classical distance. Measurement confirms that what appears isolated at the quantum level connected. Reality does not respect the separations imposed by perception or intuition. Experimental setups using entangled photons have demonstrated the phenomenon over distances exceeding hundreds of kilometers. Satellites relay entangled particles between continents, reproducing correlations that defy classical expectations. Observation confirms that these are not anomalies, errors, or artifacts of experimental design. The correlations are precise, predictable, and inherent to the quantum nature of matter. Space is permeated by relational structure that is measurable yet invisible to casual observation. Ultimately, quantum entanglement exposes the fragility of assumptions about separateness, independence, and local causality. You navigate a macroscopic world in which objects appear discrete, yet the microscopic substrate is relational, instantaneous, and non-local. Observation confirms connections that transcend space, correlations that collapse assumptions about the independence of distant events, and relationships that defy classical reasoning. The universe, as measured, is fundamentally interconnected in ways that your intuition cannot access, revealing a structure beneath perception, where distance is relative, and reality itself is entangled. The cosmological horizon. The observable universe is bounded, not by an edge of matter, but by the speed of light and the age of the cosmos. Regions beyond this horizon exist, yet are forever inaccessible. Measurements define limits to knowledge while confirming a reality that extends beyond perception. A contradiction between certainty and incompleteness. When you look out into space, every photon reaching your eye carries information from a specific distance and a specific time. The farthest light you can detect comes from the cosmic microwave background, emitted approximately 380,000 years after the Big Bang. Beyond that, space continues, yet photons from more distant regions have not had time to reach you. Measurement establishes a clear boundary. Andresow, observable radius of roughly 46 billion light-years, defined by the finite speed of light and the finite age of the universe. Beyond this radius, no signal can reach you, and no direct observation is possible. The horizon is not a physical barrier. Matter and energy continue beyond it. Galaxies, stars, and structures exist in regions you can never access. Their existence is inferred indirectly through cosmological models, expansion measurements, and the uniformity of the cosmic microwave background. You can calculate their properties with precision, yet every observation is mediated by the constraints of the horizon. Measurement confirms the presence of something beyond, while simultaneously defining the absolute limits of what can ever be known. This creates a tension between knowledge and reality. You can extrapolate the distribution of matter, the evolution of galaxies, and the likely structures beyond the horizon. Yet these remain fundamentally unobservable. Predictions can be highly precise, yet they do not equate to experience. The universe extends infinitely in principle, or at least far beyond the observable portion. And yet, you are constrained by a sphere of access defined by light speed propagation. The horizon enforces a permanent incompleteness in knowledge, even as it is measurable in its boundary. Expansion of the universe complicates this further. Distant regions are receding from you at speeds exceeding the speed of light due to the stretching of space-time itself. The expansion ensures that some galaxies currently within the observable limit will eventually cross beyond your reach, slipping outside causal contact forever. Measurement of the Hubble constant and cosmic redshifts confirms this trend. The horizon is dynamic. It grows, but it also imposes limits. And the growth of space itself creates regions permanently inaccessible, confirming that part of reality is inherently unreachable. The cosmological horizon also reframes the concept of causality. Events beyond the horizon cannot influence you in any observable way. You can calculate the likely events that occur in these regions, but measurement cannot confirm them. Reality exists without interaction, independent of observation, yet the evidence of its structure is encoded only indirectly in the measurable universe. The observable and the inaccessible are entwined. Light from the edges carries the imprint of cosmic history, yet the full expanse remains beyond verification. The paradox lies in certainty derived from incompleteness. You know the size of the observable universe, the age of its earliest light, and the dynamics of expansion. Yet these measurements define a boundary that simultaneously reveals and conceals. Reality exists in full beyond your horizon. Yet every observation you make is bounded by what can reach you. You measure a universe with finite access to its infinity, confirming existence while encountering permanent limits to knowledge. Ultimately, the cosmological horizon confronts you with the fragility of perception. Measurement and theory provide certainty about boundaries, yet confirm a universe that is, in principle, larger more complex, and forever beyond direct experience. The observable and the inaccessible coexist, a measurable contradiction embedded in space-time. You are situated in a finite sphere, witnessing a universe whose full expanse is defined but unreachable. Reality stretches beyond comprehension, yet measurement enforces an undeniable boundary, leaving certainty and incompleteness inextricably entwined. The measure problem in cosmology. Your assumptions about probability rely on counting occurrences, yet the universe may be infinite. Any ratio of observed events becomes ambiguous when the totality is unbounded. Observation yields definitive local statistics, but global understanding remains undefined, a paradox rooted in scale. When you calculate probability, you assume a finite set of possibilities. A coin has 2 outcomes. A die has 6. Observing repeated events allows you to assign meaningful ratios and predict likelihoods. The universe, by contrast, may contain an infinite number of stars, planets, and regions of space. Events that are extremely rare locally could occur infinitely often somewhere else. Observation within your finite horizon provides precise statistics, yet any extrapolation to the entire cosmos becomes ill-defined. Measurement confirms the local pattern, but global ratios have no unique definition. Consider the occurrence of life, for instance. You can estimate the probability of habitable planets or the emergence of intelligent civilizations based on stars within the observable universe. These numbers are measurable and statistically grounded. Yet if space extends infinitely, the number of potential occurrences becomes unbounded. Every event that is possible, no matter how improbable, occurs infinitely many times. Ratios, frequencies, and relative likelihoods lose meaning. Observation is valid in your local region, yet the universe as a whole resists quantification. The measure problem extends to cosmological inflation. Inflation predicts that regions of space expand at different rates, producing pocket universes with varying physical constants. Observation confirms that your local universe has specific properties, yet extrapolation to the multiverse introduces ambiguity. How do you define probabilities when the number of universes is infinite and diverse? Counting becomes impossible. Any fraction depends on the method of weighting, the choice of cutoff, or the frame of reference. Measurement within your horizon is precise, but the global picture remains undefined. A tension embedded in the structure of space itself. This ambiguity challenges assumptions about typicality and expectation. You presume that your observations are representative, that the laws, constants, and phenomena you measure are typical of the cosmos. Yet in an infinite universe, This assumption is untestable. Observation confirms local consistency, but provides no insight into what is likely or normal on the largest scales. Any statement about probability beyond your horizon becomes contingent on the arbitrary choice of measure. The paradox is measurable, persistent, and unavoidable. Even fundamental constants illustrate the issue. The strengths of forces, particle masses, and the rate of expansion are precisely measured locally. Extrapolation to infinite space raises the question of how often these values occur, or whether they are rare or typical. Local measurements are exact, yet global statistics are undefined. Probability itself becomes a tool that operates only within boundaries, and the unbounded universe undermines the certainty you rely upon. The measure problem also affects prediction. Cosmology seeks to anticipate the distribution of galaxies, matter, and energy. Within a finite volume, statistical models succeed. On infinite scales, however, all configurations compatible with physical law occur somewhere, and no single prediction can be privileged. Observation confirms local trends, yet cannot select among the infinite possibilities. The universe is simultaneously predictable and unclassifiable, a tension encoded in scale. Ultimately, the measure problem forces you to confront the limitations of knowledge imposed by infinity. Local observation provides certainty. Counts, ratios, and probabilities are meaningful within your horizon. Beyond it, the totality is undefined, resistant to classification, and unconstrained by local measurement. The universe allows precise measurement, yet denies definitive global understanding. Observation yields information, but scale imposes ambiguity. Reality is both knowable and unknowable, measurable and infinite, a contradiction rooted in the structure of the cosmos itself. The Planck scale. Discrepancy. Space and time appear continuous at macroscopic scales. Yet, at the Planck length, quantum gravity predicts discrete units. Observations of particle interactions approach but never reach this limit, hinting at a granularity that is simultaneously inferred and invisible. Reality is smooth in perception, but quantized in principle. When you move your hand or measure the passage of time, both appear continuous. Distances can be subdivided without apparent limit. Clocks tick smoothly, and rulers provide precise, arbitrarily small measurements. Your intuition aligns with the continuity of space and time, and every experience reinforces the idea of a seamless fabric. Yet theoretical physics indicates that this perception is an approximation, valid only at scales far larger than the Planck length, approximately 1.6 on 10 to 35 meters. At this scale, the smooth continuum of space-time breaks down, replaced by a discrete, quantized structure. Quantum gravity models, including loop quantum gravity and string theory, imply that space-time consists of fundamental units, indivisible and finite. These units define the smallest meaningful interval of space and time. Observation of particle interactions at high energies approaches these limits, yet no experiment can fully probe them. The granularity is inferred from theory and mathematical consistency, supported by extrapolations from measurements, but it remains beyond direct detection. Reality at this level is simultaneously known and unknowable. The discrepancy creates a tension between perception and principle. Your macroscopic world appears smooth because the Planck scale granularity is orders of magnitude below the scale of measurement. Every distance you measure, every second you observe, contains vast numbers of Planck units. Measurement confirms smoothness within accessible scales. Yet theory predicts that beneath this apparent continuity lies a discrete substrate. The universe is, in principle, digital, even as your senses and instruments record analog behavior. This granularity also has implications for fundamental physics. Singularities, such as those predicted in black holes or the Big Bang, arise from equations that assume a continuous space-time. At Planck scales, these singularities may be resolved by the discrete structure, implying a finite, quantized foundation for space and time. Observation cannot directly confirm this resolution. You can only infer it from the consistency of theory with measured phenomena. Reality presents contradictions, smooth in what you can see, quantized in what you can only calculate. Energy and momentum are similarly constrained. The smallest meaningful intervals imply limits on the precision of simultaneous measurements of position and time. Observation of particles at extreme energies approaches these boundaries, producing effects consistent with quantum uncertainty. No experiment can isolate or probe the Planck scale directly, yet every interaction hints at its existence. Reality is layered, continuous at the observable scale, discrete at the fundamental scale, and consistent across both. The discrepancy challenges the notion of continuity in causality. You assume that space and time provide a seamless backdrop against which events unfold. Yet at the Planck scale, events cannot be defined with arbitrary precision. Measurement yields smooth trajectories at human scales, but the underlying structure is a lattice of probabilities, nodes, or loops. Causality remains intact macroscopically, yet it is founded on a fundamentally discrete framework. Observation validates continuity only as an emergent phenomenon. Ultimately, the Planck scale discrepancy exposes the limits of perception and measurement. Reality is simultaneously smooth and granular, observable and inferred, continuous in experience, and quantized in principle. The universe enforces coherence across scales while concealing its smallest structure. Every measurement you make affirms the continuity you expect, yet the foundations of space and time remain, discretized beyond reach. You inhabit a world of apparent analog fluidity, underlain by an invisible digital lattice, where observation confirms one reality, while theory predicts another, and the ultimate nature of space-time remains irreducibly paradoxical. Time dilation in gravitational fields. Clocks at different altitudes tick at different rates. The stronger the gravitational field, the slower time passes. Observed with atomic precision, this effect is real and measurable. Your assumption of uniform temporal flow is violated by ordinary variations in height, a contradiction that penetrates daily experience. Time, as you perceive it, seems uniform. Seconds pass at a constant pace, clocks tick in synchrony, and your internal sense of duration aligns with the mechanical devices you trust. You assume that the flow of time is independent of location and context. Yet measurement with modern atomic clocks demonstrates that this assumption is incorrect. Clocks at higher altitudes tick slightly faster than clocks at lower altitudes. The difference is minuscule for everyday distances, but it is real, reproducible, and in precise agreement with general relativity. Observation confirms that the passage of time is not absolute, but contingent on gravitational potential. Consider a clock placed on a mountaintop compared to one at sea level. The atomic transitions defining the unit of time are identical, yet the top clock accumulates a slightly greater number of ticks over a given interval. This difference is measurable. Even a change of a few meters in elevation produces detectable temporal divergence. Observation confirms that time itself is stretched by gravitational influence, subtly undermining the expectation that seconds are the same everywhere. The macroscopic world is permeated by this effect, but human intuition rarely detects it because the magnitude is small relative to daily experience. The effect grows dramatically in stronger gravitational fields. Near a neutron star or black hole, time slows substantially compared with distant observers. Measurement of pulsars and orbital dynamics confirms predictions. Processes near these objects appear elongated when viewed from afar. Events that seem brief locally can span years when measured externally. The experience of duration becomes dependent on position within the gravitational landscape. Reality is no longer uniform. It is shaped by mass and curvature. Observation confirms the magnitude and consistency of this effect, yet it challenges every assumption of universal simultaneity. Even on Earth, the consequences are concrete. Global positioning systems rely on extremely precise timekeeping. Satellites orbiting the planet experience weaker gravity than receivers on the surface. Their onboard clocks tick faster, and without correction, navigational errors accumulate rapidly. Measurement reveals that the apparent constancy of time is a local approximation. Clocks function reliably only when relativistic corrections are applied. Observation transforms what seems an abstract principle into a tangible, operational necessity. The implications extend to your perception of causality. You assume that events are ordered identically for all observers. Time dilation demonstrates that simultaneity is relative. Two events judged simultaneous at one altitude are no longer simultaneous at another. Measurement confirms that temporal order is observer-dependent, a subtle but inescapable violation of intuitive notions of sequence. Reality, as experienced, is contingent upon gravitational context. The effect also forces a reconsideration of the universality of experience. Human life unfolds under relatively uniform conditions of gravity, creating the illusion of a single, shared temporal flow. Measurement shows that this flow is only locally consistent. Clocks, chemical reactions, and biological processes all respond to gravitational time dilation, subtly varying in rate according to position. Observation reveals that uniformity is emergent, not fundamental. Ultimately, time dilation in gravitational fields exposes the fragility of your assumptions about temporal uniformity. Measurement confirms that time is not a universal parameter, but a variable influenced by mass and space. Your perception of a constant flow is local and approximate. The universe enforces consistency in principle, yet observation reveals variation in reality itself. Seconds are not the same everywhere. Duration is not absolute. Time, which you experience as linear and continuous, is conditional, context-dependent, and measurable in its variation. Reality does not flow uniformly. It bends under the weight of gravity, and you inhabit a world where the passage of time itself is an observable, quantitative, and profoundly relative phenomenon. The horizon, problem regions of the cosmic microwave background, share near identical temperatures despite being causally disconnected. Observation reveals uniformity that should not exist, suggesting mechanisms of correlation beyond standard cosmology. Measurement contradicts expectation without providing a clear solution. When you examine the cosmic microwave background, you are looking at radiation emitted roughly 380,000 years after the Big Bang. Every region of this primordial light carries information about conditions at that epoch. You assume that the temperature of one region depends only on processes that could have influenced it through causal contact, through the transmission of energy, particles, or radiation. Yet measurement reveals a near uniform temperature across regions so widely separated that, according to the speed of light and the age of the universe, they could never have exchanged information. Observation exposes a coherence that should be impossible. The paradox emerges from standard cosmology. Light travels at a finite speed. In the time available before the emission of the cosmic microwave background, regions separated by more than a few degrees in the sky could not have influenced each other. There is no classical mechanism for equilibration. The temperature of one region should be independent of the temperature of a distant, causally disconnected region. Yet when you measure the sky, you find differences of only a few parts in 100,000. Observation confirms the uniformity, but expectation predicts variation. Measurement and intuition are in conflict. Inflation theory offers a proposed resolution. An early epoch of exponential expansion stretched a small, initially uniform region to encompass the observable universe. Observation is consistent with this. The CB is smooth, fluctuations are small, and the large-scale distribution of matter aligns with predictions. Yet the mechanism is inferred rather than directly observed. Measurement confirms uniformity, but the processes responsible lie beyond empirical access. The paradox is not fully resolved. The evidence is indirect, and the causal explanation remains partially theoretical. The implications are unsettling. You inhabit a universe in which vast regions exhibit correlated properties without causal interaction. The homogeneity of the cosmic microwave background is measurable, precise, and reproducible. Yet the underlying mechanism that enforces this correlation is inaccessible to direct experiment. Reality, as observed, exhibits order that classical causality cannot account for. Observation confirms the paradox. Uniformity without contact, structure without interaction. The horizon problem also constrains your understanding of probability and initial conditions. If regions could not interact, then the observed uniformity is statistically improbable. Yet it occurs. Measurement validates this improbability repeatedly. Every observation reinforces the same contradiction. The universe is orderly at scales where disorder would be expected. The assumption that distant regions evolve independently is violated by empirical evidence. Reality behaves as though initial conditions or processes enforced correlation on scales inaccessible to classical mechanisms. The paradox persists in other observational phenomena: large-scale anisotropies, baryon acoustic oscillations, and the distribution of galaxies are all consistent with the uniformity encoded in the cosmic microwave background. Measurement confirms coherence across multiple independent data sets. Yet the causal basis of that coherence remains beyond observational reach. You witness order, measure it precisely, and yet the explanation is inferred, hidden, and fundamentally inaccessible. Ultimately, the horizon problem exposes the tension between causality, measurement, and expectation. Observation confirms uniformity at scales where classical mechanisms predict independence. Reality presents a system in which widely separated regions share properties they could not have communicated to achieve. You confront the measurable fact of coherence without access to its mechanism, a contradiction embedded in the structure of space-time itself. Measurement verifies the paradox, and the universe remains ordered in a way that is both observable and inexplicably beyond causal explanation. The black hole firewall debate. Classical general relativity predicts a smooth event horizon. Quantum mechanics implies that infalling matter could encounter high-energy phenomena. A firewall. Observation supports black hole behavior in both frameworks. Yet the paradox between these measurements remains unresolved. When you consider a black hole, you imagine a boundary from which nothing escapes: the event horizon. Classical general relativity describes this surface as smooth and uneventful. An object falling through the horizon would not notice any immediate disruption. The equations of Einstein predict that space-time curvature is extreme near the singularity, but the horizon itself is locally unremarkable. Observation of orbits near black holes, gravitational lensing, and the dynamics of accretion disks confirm this smooth behavior. The event horizon, by all classical accounts, is a region of continuity. Quantum mechanics introduces a different perspective. The principle that information cannot be destroyed implies that the horizon must encode information about infalling matter. If information is preserved, the horizon cannot remain smooth in all frames of reference. Theoretical calculations suggest that infalling matter might encounter a firewall, high-energy quanta, that destroy it and release the encoded information. Observation of Hawking radiation, while indirect, is consistent with the evaporation of black holes and the release of information, implying that quantum effects are active at the horizon. Measurement confirms phenomena predicted by both relativity and quantum mechanics. Yet the two frameworks are in direct tension at this boundary. The paradox is measurable in principle. Gravitational wave observations of merging black holes, high-resolution imaging of the shadows of supermassive black holes, and spectral analysis of accretion disks all match predictions of general relativity. Yet the principles of quantum mechanics cannot be ignored. Information conservation is experimentally validated across particle physics, and the theoretical necessity of a firewall arises from well-established calculations. Reality thus presents a situation in which both a smooth horizon and a high-energy horizon are supported by measurement, but no single framework accommodates both simultaneously. You perceive the horizon as a limit to what can be observed. Light cannot escape, and direct measurement of internal structure is impossible. Yet indirect observation of black hole mass, spin, and radiation provides evidence of processes occurring at or near the horizon. These measurements confirm extreme gravitational effects and quantum phenomena, without revealing the definitive mechanism by which information is preserved. Observation affirms the existence of the paradox. Measurable consequences exist on both sides of a contradiction that cannot be resolved with current experimental access. The firewall debate also challenges assumptions about locality and causality. Classical reasoning assumes that events at the horizon are local, experienced only by the infalling observer. Quantum reasoning implies that effects are global, influencing the encoding of information across space-time. Measurement verifies both the local smoothness and the non-local preservation of information. Reality behaves as though space-time simultaneously permits a continuous crossing and a destructive energetic barrier, depending on which aspect is measured. Implications extend beyond theoretical black holes. The debate informs the fundamental structure of space-time, the nature of information, and the limits of observation. You rely on measurement and theory to understand distant phenomena, yet black holes reveal a boundary where observation alone cannot reconcile competing frameworks. The paradox is embedded in the data. Gravitational waves, light curves, and radiation patterns are consistent with smooth horizons, while the principles underpinning quantum mechanics suggest a fundamentally incompatible structure. Ultimately, the black hole firewall debate exposes the tension between two pillars of physics. Observation validates the predictions of both classical relativity and quantum mechanics, yet their conjunction is unresolved. You witness behavior that is simultaneously smooth and potentially destructive, measurable yet paradoxical. The horizon enforces limits on access, yet reveals contradictions inherent in the nature of information, space-time, and reality itself. Measurement confirms the existence of the paradox, and the universe allows both sides to coexist in principle, leaving the ultimate nature of the horizon indeterminate and profoundly unsettling. The bootstrap paradox. Objects or information can, in theory, exist in a self-originating loop, violating conventional causality. Time travel thought experiments demonstrate that a measured effect can precede its cause, a logical possibility permitted by relativity and quantum constraints. Observation does not permit resolution, only recognition of inconsistency. You assume that every event has a cause, and that causes precede effects in a linear sequence. Your intuition aligns with everyday experience. Objects are created, information is transmitted, and outcomes follow inputs. Yet theoretical physics allows scenarios in which this sequence is violated. Relativity permits closed time-like curves, paths through space-time that return to their own past. Quantum mechanics allows states to evolve in ways that do not strictly distinguish between cause and effect in certain contexts. Observation confirms that these scenarios are logically consistent, even if they contradict ordinary temporal intuition. Consider a piece of information, such as a scientific discovery, that appears in your time but originates from the future. You receive it, record it, and eventually transmit it back through a hypothetical time loop. The information exists, yet it has no identifiable point of creation. Measurement of the looped process, if it were possible, would confirm the existence and integrity of the information at all stages. Yet causality appears violated. The effect exists before the cause, a self-consistent but paradoxical sequence. Observation can track the presence of the information, but cannot identify an origin within the loop. Reality allows the object or information to exist without a conventional source. The paradox extends to objects as well as information. A device, book, or particle could theoretically traverse a closed time-like curve, appearing in your timeline without ever having been created outside the loop. Observation would confirm its presence at each stage within the loop. Its properties, measurable and consistent. Yet conventional reasoning fails. The object has no point of initial creation. Measurement validates existence, but cannot resolve origin. The universe, under the rules of relativity and quantum mechanics, permits coherent systems in which causality is non-linear, while observation exposes the incompleteness of conventional explanation. The bootstrap paradox also challenges assumptions about determinism. You assume that outcomes can be traced backward to initial conditions. In a looped timeline, initial conditions themselves are undefined. They exist only within the cycle. Observation might reveal the consistency of the system at every temporal point, yet the absence of an identifiable origin means that determinism becomes a local property rather than a global principle. Reality enforces consistency within the loop, but the notion of a beginning becomes meaningless. Measurement confirms effect without cause, a logically permissible yet deeply unsettling situation. Implications extend to your understanding of time itself. The passage of seconds, minutes, and hours is intuitive and linear in daily life, yet in scenarios permitting closed time-like curves, time is no longer strictly ordered. Observation can verify sequences of events, but the causal relationships underlying them may be inverted or circular. You confront a universe in which linear temporality is emergent and local, rather than absolute and universal. Measurement validates this emergent order without providing insight into the underlying structure, leaving causality intact only in appearance. Ultimately, the bootstrap paradox exposes a tension between observation, causality, and logical possibility. You can measure the presence of objects or information within a loop, confirm their consistency, and predict their behavior. Yet their origin is undefined, their cause inaccessible, and the temporal ordering inverted. Reality permits a sequence that is internally coherent, yet externally paradoxical. Observation affirms existence without origin, consistency without cause, and logical possibility without conventional temporal structure. The universe accommodates loops in space-time, measurable and precise, that defy ordinary intuition, leaving causality unsettled and fundamentally ambiguous. The vacuum catastrophe. Quantum field theory predicts an energy density of empty space vastly higher than observed. Measurements of the cosmological constant reveal a discrepancy of 120 orders of magnitude. Reality confronts expectation in a manner both precise and profoundly counterintuitive. You assume that empty space is, by definition, inert, a vacuum devoid of activity. In daily experience, absence of matter implies absence of measurable effects. Yet quantum mechanics demonstrates that even the emptiest regions of space are seething with virtual particles and fluctuating energy. The vacuum is not empty. It is a dynamic entity, with calculable energy contributions arising from zero-point fluctuations of quantum fields. Theoretical calculations provide a definite number, an expected energy density of space. Observation, however, reveals a value unimaginably smaller. Measurement confirms the presence of a cosmological constant, but the magnitude is minuscule compared to predictions. the discrepancy is enormous. If the vacuum energy predicted by quantum field theory were realized, the universe would have either collapsed almost immediately after the Big Bang or expanded so rapidly that galaxies could never form. Observation confirms neither outcome. Galaxies, stars, and planets exist, and the universe has persisted for 13.8 billion years. Measurement validates a tiny but positive cosmological constant, consistent with the observed accelerating expansion of the universe. Yet the theoretical expectation is catastrophically off. A difference of 120 in scale. Reality presents a universe finely balanced between explosive expansion and gravitational collapse, in a manner that defies precise calculation from first principles. The paradox also highlights the tension between scales. Quantum field theory operates at subatomic levels, predicting fluctuations and vacuum contributions that are measurable in principle, but not directly observable at human scales. Cosmology measures expansion, gravitational effects, and the energy density of space on galactic and intergalactic scales. Observation connects the macroscopic to the microscopic, yet the extrapolation from quantum mechanics to cosmology fails by an almost inconceivable margin. Measurement is precise at both ends, yet the numbers are incompatible. Reality behaves coherently in observation, yet its theoretical foundation predicts an impossible instability. Attempts to reconcile the discrepancy deepen the tension. Supersymmetry, string theory, and modifications to gravity provide frameworks that could, in principle, cancel the predicted vacuum energy, producing the tiny cosmological constant observed. Yet none of these frameworks has been confirmed experimentally. Observation validates the measured value, but not the mechanism. The universe remains orderly, stable, and persistent, even as theory predicts a catastrophic imbalance. Measurement demonstrates consistency, while expectation fails by a factor beyond comprehension. The vacuum catastrophe challenges assumptions about causality, scale, and the relationship between theory and measurement. You assume that calculation and observation will align within reasonable tolerance, especially when based on well-tested physical principles. Yet in this instance, they diverge by a factor that is precisely measurable and mathematically robust. Reality is simultaneously predictable in its expansion and profoundly unexpected in its underlying energy distribution. Observation confronts theory with a paradox so extreme that it is unsettling in both magnitude and implication. Ultimately, the vacuum catastrophe exposes a deep and unresolved tension between quantum mechanics and cosmology. You measure a universe that expands slowly, steadily, and in accordance with a small cosmological constant. You calculate, using the best understanding of quantum fields, a value that should obliterate that universe almost instantly. Observation confirms what exists. Theory predicts what should exist. The discrepancy is real, measurable, and precise, yet it remains without explanation. Reality reconciles itself in observation while defying every expectation derived from fundamental calculation, leaving a gulf between knowledge and measurement that is both exact and profoundly counterintuitive. The measurement problem. The act of measuring a quantum system fundamentally alters its state. Observation is not neutral. It defines what is real. You assume that seeing is passive, yet every measurement becomes an interaction, a collision between expectation and reality itself. At the scale of everyday objects, observation seems straightforward. You look at a chair, read a thermometer, or record the speed of a car. Your instruments report values that correspond to an underlying reality independent of your act of measurement. You assume that measurement merely reveals, without influencing, the state of the system. Quantum mechanics undermines this assumption. Observation at the microscopic scale does not passively record. It actively collapses possibilities into a single outcome. Measurement defines reality in a way that is both predictable statistically and fundamentally non-deterministic individually. Consider a particle in a superposition, existing in multiple positions simultaneously. Until you measure it, the particle does not occupy a single location. It is described by a wave function that encodes all possible positions. The act of measuring position forces the particle into one definite state. Observation selects reality from probability. Measurement is not a neutral lens. It is a causal intervention. What you record is a product not only of the particle's prior state, but also of your interaction with it. Observation and existence are inseparable. Experiments confirm this behavior repeatedly. The double-slit experiment illustrates the paradox clearly. A particle passing through two slits produces an interference pattern, if unobserved, consistent with wave-like behavior. When detectors measure which slit it passes through, the interference pattern disappears, and the particle behaves like a discrete object. Observation alters the outcome. Measurement does not simply report reality, it shapes it. Your expectation of passive observation is violated by experimental evidence. Reality is conditional upon interaction. The measurement problem also exposes the tension between microscopic and macroscopic worlds. Macroscopic objects appear stable and well-defined. A chair or a rock occupies a single position, independent of observation. Yet these objects are composed of particles that individually behave according to quantum rules. Measurement produces well-defined states locally, but the underlying substrate is inherently probabilistic. Observation collapses possibilities at the small scale, producing the deterministic behavior you experience. Measurement enforces classical reality emergently, but the underlying processes remain uncertain. Time, causality, and predictability are all affected. You assume that events unfold independently of whether they are observed. In quantum systems, the act of measurement defines the state from which future evolution proceeds. Observation alters not only what is known, but what is real, influencing subsequent dynamics. Measurement is an intervention in the chain of causality, creating a subtle but inescapable distinction between observed and unobserved systems. Even in thought experiments, the implications are profound. Schrödinger's cat illustrates a macroscopic superposition. A cat is both alive and dead until observed. Measurement forces a definite outcome. Observation is inseparable from existence, collapsing ambiguity into a single reality. Measurement becomes not a passive act of recording, but an active process that determines the state of the universe at that point. Ultimately, the measurement problem exposes the fragile interface between observer and observed. You assume that reality exists independently and can be catalogued without disturbance. Observation at the quantum level disproves this assumption. Every measurement is an interaction, a boundary where expectation and reality collide. Measurement defines the outcome, shapes the system, and produces certainty from probability. Reality is conditional, contingent, and inseparable from observation itself. You witness the world not as a neutral observer, but as a participant in the fundamental definition of existence, where knowing and being are intertwined inextricably and irreversibly. The arrow of entanglement. Information spreads in ways that violate classical intuitions about locality. Entanglement produces correlations that propagate without traditional communication. Observation confirms non-local effects, yet no classical causal pathway exists. The direction of influence remains undefined. You assume that influences propagate through space in a sequential, measurable way. Signals travel from point A to point B at finite speed, bound by the speed of light. Causes precede effects in space and time. Yet entanglement contradicts this assumption. When two particles become entangled, their properties become linked in such a way that measurement of one immediately constrains the state of the other, regardless of distance. Observation repeatedly confirms this non-local correlation. The particles exhibit connected behavior without any discernible medium, without any classical signal bridging them. The paradox is measurable. Experiments have separated entangled particles by kilometers, even hundreds of kilometers, and recorded correlations that violate Bell's inequalities. The outcomes are not due to pre-existing states or hidden variables, as extensive testing confirms. Measurement validates that the effect occurs instantaneously, yet no observable mechanism transmits the influence. Reality demonstrates a relationship that exists beyond conventional understanding of space and time. Observation verifies the correlation, yet the pathway and direction of influence remain undefined. Entanglement also challenges notions of information propagation. You assume that information can be transmitted only through causal, localized interactions. Observation shows that entangled systems defy this assumption. The measurement of one particle provides information about the other, without any classical communication channel. The non-locality is not a failure of theory, but an intrinsic property of the quantum state. Measurement confirms the phenomenon. Yet the classical frameworks of causality, distance, and temporal order cannot account for it. Reality functions on principles that exceed your conventional understanding of influence. The arrow of entanglement complicates temporal reasoning. You might expect that one particle's measurement precedes and determines the other's outcome. Experiments show that the temporal ordering of measurements does not affect the correlations. Whether you measure particle A before particle B or vice versa, the statistical correlations remain identical. Observation confirms the effect, yet time provides no preferred direction for the propagation of influence. The arrow of entanglement is not aligned with the arrow of classical causality. Measurement exposes a non-classical structure where correlations exist without temporal hierarchy. Even in macroscopic terms, the consequences are subtle but real. Entanglement underlies quantum computing, cryptography, and emerging technologies. Observation verifies that entangled systems maintain coherence over long durations and distances. The effect is real, measurable, and operational, yet it violates the expectation that spatial separation implies independence. The arrow of influence cannot be localized. Reality enforces consistency across space while eluding classical mechanisms. Measurement confirms connection without communication. Ultimately, entanglement exposes a fundamental tension between observation, causality, and the classical notion of locality. You assume that the universe operates through sequential interactions within space and time. Observation demonstrates that this assumption is limited. Correlations can exist across vast distances instantaneously, without a discernible channel. The arrow of entanglement defines influence in a way that is real, measurable, and consistent, yet independent of conventional causality or temporal direction. Reality enforces coherence without classical mediation, leaving observation to confront a system that is intimately connected, fundamentally non-local, and irreducibly paradoxical. Measurement confirms the effect. It does not explain the mechanism. You witness correlations that defy expectation. Correlations that are directional only in principle, yet timeless in practice, revealing a universe in which the familiar rules of influence and causality are neither violated nor satisfied, only subtly reframed. The infinite regress of observation. Every measurement assumes a reference frame, but the act of defining a frame is itself an observation. Observations depend on other observations, creating an unresolvable hierarchy. Measurement exists, yet its foundation cannot be firmly established. You assume that when you measure, you are observing an objective system from a neutral perspective. A clock records time, a ruler measures distance, an instrument records energy. Each measurement seems grounded, absolute, and independently verifiable. Yet, every reference frame you use, spatial, temporal, or otherwise, is itself established through observation. To define a coordinate system, you measure physical markers. To calibrate a clock, you compare it to other clocks. Each act of measurement rests on a prior measurement. Observation is layered upon observation, a hierarchy with no ultimate starting point. The regress becomes apparent when you attempt to define fundamental constants. The speed of light, Planck's constant, or the gravitational constant are all defined through measurement. Each experiment relies on a frame established by previous measurement, and every calibration references prior observations. Observation validates subsequent observation, yet its foundation is never absolute. Measurement exists as a reliable procedure, but the ultimate grounding of that procedure is inherently recursive. Reality provides certainty at operational levels, yet simultaneously conceals the origin of that certainty. Consider quantum mechanics, where measurement alters the system. Observation of a particle assumes a defined laboratory frame. That frame is itself a physical system, subject to the laws of physics. Its coordinates, timekeeping, and reference points are products of prior observation. If each measurement is contingent on another, then there is no ultimate observer-independent foundation. Observation is real and precise, yet conceptually unanchored. Measurement exists, but the hierarchy upon which it depends extends indefinitely backward. The infinite regress also affects relativity. Defining simultaneity, spatial separation, or velocity requires a chosen frame of reference. Observers moving relative to each other measure time and space differently. Each observer relies on measurement to establish the frame, yet the choice of frame is itself an act of observation. Observation validates local measurement, yet cannot produce an absolute frame-independent foundation. Reality appears coherent locally, but remains contingent on the reference frame, and the hierarchy of observation extends without termination. The implications are unsettling. You encounter a universe in which measurement is both precise and conceptually provisional. Every outcome is well defined within a frame, yet the hierarchy beneath that frame is unresolvable. Observation produces certainty in practice, but cannot establish ultimate justification in principle. Measurement, in essence, is both real and epistemologically dependent. You trust your instruments, yet the confidence they provide rests on a chain of observations that extends without a foundational terminus. Even at the cosmological scale, the problem persists. Observing distant galaxies, measuring cosmic microwave background radiation, or mapping large-scale structure all depend on reference frames defined by local physics and prior calibration. The infinite regress is embedded in the structure of observation itself. Measurement is possible, precise, and operationally effective, yet its conceptual foundation is never directly observable. Observation exists, yet the certainty of its origin is perpetually deferred. Ultimately, the infinite regress of observation reveals the fragility of knowledge itself. You assume that measurement provides a grounded account of reality. Observation confirms phenomena, produces reproducible outcomes, and establishes patterns. Yet the hierarchy upon which these observations rest cannot be terminated or fully justified. Measurement is simultaneously exact and conceptually unanchored. Reality allows observation to function with precision, while concealing the ultimate origin of that precision. Every observation rests upon another, extending backward indefinitely, a structure of infinite dependence that measurement can navigate but never fully resolve. Observation exists. Its foundation does not. The paradox of quantum, Zeno. Continuous observation can effectively freeze a system's evolution. Experiments confirm this watched pot effect in quantum systems. Time proceeds externally, yet within the observed system, change is suspended. Perception and measurement diverge in real, measurable ways. You assume that a system evolves continuously over time. A radioactive atom decays, a particle moves, a chemical reaction proceeds. Seconds pass, and processes unfold according to the governing laws. Yet quantum mechanics demonstrates that frequent measurement alters this natural evolution. When a quantum system is observed repeatedly, the probability of it changing state decreases. If observed continuously, the system can be effectively frozen in its initial state. Measurement interferes with temporal evolution. Observation becomes a constraint on reality itself. Experiments confirm the effect with precision. Unstable particles, trapped ions, and two-level quantum systems exhibit inhibited transitions when monitored. Measurement is not passive. It is an active boundary condition. The system evolves as expected in the absence of observation. But the act of measurement interrupts that evolution, creating a divergence between the external flow of time and the internal dynamics of the observed system. Reality becomes conditional. What occurs depends on the act of observation. The paradox challenges the assumption that time's passage is universal and independent of the observer. External clocks tick normally, and the universe continues its processes undisturbed. Yet, within the observed system, temporal progression is suspended. Measurement imposes a local rule, one that diverges from the ordinary experience of time. Observation defines not only what is known, but what occurs. Reality unfolds differently, depending on the presence of an observer. A phenomenon, measurable, repeatable, and in agreement with quantum theory. Even minimal interactions can produce the effect. A system observed intermittently experiences slowed evolution proportional to the frequency of measurement. The more often a state is probed, the less likely it is to change. Observation and temporal evolution are entwined. Measurement dictates outcome probabilities, constraining the system's dynamics. Perception of continuous change exists externally, yet the internal state remains suspended. Time is not a singular, absolute parameter. It is contingent on interaction. The quantum Zeno effect also emphasizes the tension between microscopic and macroscopic worlds. Large objects do not appear frozen under continuous observation because their internal states are effectively averaged over innumerable interactions. Yet at the scale of a single particle or atom, measurement exerts direct influence. Observation enforces stability, producing predictability at the cost of natural evolution. Measurement collapses. Probability, dictating the course of events. Time within the system does not pass independently of observation. Reality is partially defined by the act of being watched. Implications extend to the interface between theory and experience. You trust that physical systems have independent dynamics, that time flows continuously, and that measurement merely reveals this flow. The paradox demonstrates that at the quantum level, observation and evolution cannot be separated. Measurement is both a revelation and an intervention, creating a disconnect between external and internal temporal experience. Time, as perceived, diverges from time as realized within the measured system. Ultimately, the paradox of the quantum Zeno effect exposes a subtle but profound tension between observation, temporal evolution, and reality itself. Measurement is no longer neutral. It defines the dynamics of the system, constraining change in real, observable ways. You witness time proceed externally, yet within the observed quantum system, change can be suspended. Observation and evolution, measurement and reality diverge in a manner that is precise, measurable, and irreducibly paradoxical. The universe enforces coherence externally, while permitting local suspension internally, revealing the fragility of assumptions about time, change, and the independence of observed systems. You perceive continuity. Measurement imposes stasis. Reality accommodates both simultaneously. The Gibbs paradox. Mixing identical gases produces a change in entropy according to classical calculation. Quantum treatment corrects this, but the boundary between distinguishable and indistinguishable particles remains subtle. Observation confirms both principles depending on the framework, producing a clash of interpretations. You assume that entropy measures disorder in a straightforward, continuous manner. A system transitions from less probable to more probable configurations, and mixing produces a measurable increase in disorder. Classical thermodynamics formalizes this intuition. If you mix two containers of the same gas, classical equations predict an increase in entropy, as though the particles are distinguishable. Observation of macroscopic properties aligns with this calculation. Pressure, temperature, and density appear unchanged, yet the formal entropy expression suggests an increase, a contradiction between measurable effect and theoretical prediction. Quantum mechanics introduces a correction. Particles of the same type are fundamentally indistinguishable. The formal counting of states must account for this symmetry, reducing the calculated increase in entropy to zero when identical gases mix. Observation at the quantum level confirms this indistinguishability. No new states are created when truly identical particles interact. Measurement validates both frameworks. Classical thermodynamics works for practical macroscopic prediction, while quantum treatment captures fundamental principles, Reality supports both, depending on the lens through which it is examined. Yet the reconciliation is subtle and conceptually unsettling. The paradox arises at the interface between scales. Macroscopic measurement detects changes that classical equations predict, but fails to detect the microscopic symmetry responsible for the quantum correction. Observation confirms consistency within each framework, yet exposes a mismatch between description and underlying ontology. The system behaves coherently, yet your theoretical interpretation depends on which rules you apply. Measurement does not resolve the tension. It only highlights that entropy is simultaneously context-dependent and absolute in principle. Even when the gases are nearly identical, but not perfectly so, observation reveals gradual transitions between the classical and quantum regimes. Entropy change becomes a function of distinguishability. Measurement confirms that small differences in particle properties produce measurable effects, while perfectly identical particles produce none. The boundary is continuous in practice, yet discrete in principle. Reality enforces both continuity and quantization, depending on the framework and the scale of observation. The Gibbs paradox also challenges your assumptions about objectivity. You might expect that entropy, as a physical quantity, has a single, unambiguous value for any system. Yet observation demonstrates that entropy is dependent on your knowledge, your labeling of particles, and your theoretical framework. Measurement produces results consistent with your framework, but the underlying system admits multiple valid descriptions. Reality behaves consistently under measurement, yet defies singular interpretation. Observation exposes a duality between practical calculation and fundamental principle, a subtle but inescapable tension. The paradox further emphasizes the interplay between measurement, perception, and theory. You rely on observation to validate equations and intuitions. Macroscopic measurement aligns with classical entropy calculations, yet quantum principles dictate that the underlying state counting is different. Observation confirms each perspective internally, but their conjunction produces conceptual tension. Measurement reveals reality in its operational consistency, while simultaneously exposing a boundary where frameworks clash. Ultimately, the Gibbs paradox reveals a fundamental subtlety in your understanding of order, disorder, and indistinguishability. You measure effects, record data, and apply statistical laws, yet the foundational meaning of entropy remains context-dependent. Observation confirms both classical and quantum predictions, yet no single description is universally privileged. Reality is simultaneously consistent and conceptually fractured. Measurement verifies outcomes, yet exposes the delicate interface between distinguishable and indistinguishable, between classical intuition and quantum principle. Entropy exists. Its interpretation does not resolve cleanly. Observation affirms, yet paradox remains. The problem of fine-tuning. Fundamental constants of nature appear precisely adjusted to allow complexity. Observations indicate these values are measured with astonishing accuracy, yet theory provides no mechanism for this specificity. Reality permits existence, yet offers no causal explanation for the parameters that make it possible. You assume that physical laws and constants are arbitrary, or at least unconstrained by necessity. Gravity, the strength of electromagnetic interaction, the ratio of particle masses, the cosmological constant. These numbers could, in principle, take a wide range of values. Observation confirms that they do not. Instead, they exist within a narrow window, compatible with the formation of stars, the stability of atoms, and the emergence of complex chemistry. Measurement shows precision so exact that even minute deviations would produce a universe incapable of sustaining long-term structures. Reality allows life, yet provides no explanation for why the numbers fall within the extraordinarily tight range required. The paradox deepens when you consider scale. The universe is vast, yet the constants that govern it are finely calibrated. Slight variations in the strength of nuclear forces, for example, would prevent the formation of carbon or oxygen. Changes in the cosmological constant would lead to rapid expansion or collapse, precluding galaxy formation. Observation confirms that the values measured are both precise and consistent across space and time. Yet no mechanism within current theory accounts for why they are not otherwise. Measurement validates the parameters. Theory does not explain their existence. Reality produces a coherent, habitable universe, but does so in a manner that seems improbably specific. You encounter another layer of tension when considering probability. The odds of selecting constants compatible with complex structures by random variation are vanishingly small. Observations indicate that the values are within these improbable ranges. Reality presents a system in which extreme precision is not just present, but necessary for the features you observe. Measurement provides exact numbers, yet does not illuminate the origin of their specificity. The paradox is that the universe exists as it does, while the theoretical framework provides no causal reason for the observed tuning. Fine-tuning also challenges assumptions about universality. You assume that physical constants are simply given, fixed, or determined by deeper principles. Observation allows no direct inference about necessity. The constants are what they are, without measurable deviation. Any small change would render structures impossible. Reality behaves as though it were configured to permit complexity, yet this configuration is entirely empirical. Measurement confirms it. Explanation remains absent. The constants are simultaneously observed, operational, and conceptually enigmatic. The paradox intersects with cosmology and the structure of the universe. Observing distant galaxies, the cosmic microwave background, and the distribution of matter reinforces the same fine-tuned parameters. Measurement shows that the universe is uniform and consistent, that the laws are coherent and allow intricate phenomena to emerge. Yet the fundamental origin of these numbers is beyond reach. Reality is both orderly and contingent, precise yet unexplained. Observation confirms the consistency. Theory does not provide the why. Ultimately, the problem of fine-tuning reveals a tension between empirical measurement and theoretical causality. You witness constants that permit complexity and stability, values that are exact, precise, and persistent across the observable universe. Yet there is no explanation grounded in known mechanisms for why these numbers have been realized instead of others. Reality is intelligible in measurement, yet opaque in origin. Observation validates the possibility of existence, but the causal reason for the parameters that allow it remains unresolved. The universe is coherent and comprehensible in practice, yet conceptually fragile. Measurement affirms what exists. Explanation leaves it profoundly enigmatic. The holographic principle. Information in a volume of space may be encoded entirely on its boundary. Observations of black holes support this principle, suggesting that three-dimensional reality is emergent from two-dimensional data. Perception of space conflicts with the information contained within it, a measured paradox of scale and dimensionality. You assume that the universe is fundamentally three-dimensional. Objects occupy space in a straightforward way, and information about them is distributed throughout the volume they inhabit. Observation confirms that this is an effective description at macroscopic scales. Planets, stars, and galaxies occupy regions of space, and measuring their properties within that volume produces consistent results. Yet theoretical and observational insights from black hole physics reveal a more subtle structure. The maximal entropy of a black hole is proportional not to its volume, but to the area of its event horizon. Measurement validates that the information content of a black hole scales with surface area, implying that the three-dimensional interior is a projection of two-dimensional data. Reality does not conform to intuition. The holographic principle extends this insight beyond black holes. Cosmological considerations suggest that the information describing any spatial region can, in principle, be encoded on its boundary. Observations of gravitational effects, horizon behavior, and entropy distribution support this framework. Measurement confirms that the universe behaves as if the bulk information is constrained by two-dimensional surfaces. You perceive volumetric reality. Yet the underlying information resides on a boundary. Observation reveals a tension between the emergent experience of space and the fundamental storage of information. At a practical level, this creates paradoxes in scale and density. You assume that information about a system is proportional to the space it occupies. The holographic principle demonstrates that this assumption is violated at extreme densities or in the presence of strong gravitational fields. Black holes encode vast amounts of data on a two-dimensional surface, far more than would be expected if information were distributed volumetrically. Observation confirms that the encoding is precise and consistent. Entropy calculations, Hawking radiation measurements, and horizon area determinations all match theoretical expectations. Reality organizes itself in ways that defy naive spatial intuition. The principle also challenges assumptions about locality and emergence. You assume that information about an object is distributed locally, within the volume it occupies. Observation of holographic systems shows that information is delocalized, encoded on a distant or bounding surface. The apparent interior is emergent, reconstructed from the two-dimensional encoding. Measurement validates both the emergent perception of three-dimensional space and the underlying two-dimensional encoding simultaneously. The paradox is not theoretical alone. It is empirically grounded in entropy calculations and black hole physics. Reality supports two contradictory yet consistent perspectives: the experienced interior and the encoded boundary. Implications extend to the nature of reality itself. You experience a universe of continuous space, full of depth and extension. Observation confirms that this three-dimensional experience is operationally effective, yet fundamentally emergent. Measurement of black holes and horizon areas confirms the limits on information density. The universe reconciles volumetric experience with a surface-based informational architecture. Observation validates both levels: macroscopic perception and microscopic encoding. Yet their relationship is counterintuitive. Reality is simultaneously three-dimensional and fundamentally two-dimensional, measurable, and consistent, yet conceptually paradoxical. Ultimately, the holographic principle exposes a profound tension between perception, measurement, and information. You can navigate space, measure volume, and interact with objects in 3 dimensions. Observation confirms that the information underlying these interactions resides on boundaries, encoded in a manner consistent with both quantum theory and general relativity. Perception of space conflicts with the fundamental encoding of reality, yet both coexist without contradiction. Measurement validates emergent 3-dimensional experience while revealing a deeper 2-dimensional substrate. Reality allows space to exist as both extension and projection, simultaneously experienced and encoded. A paradox of dimensionality, scale, and information that is precise, measurable, and fundamentally unsettling. The simulation-like regularity. Physical laws exhibit consistency and mathematical simplicity across vast scales. Observations reveal a universe governed by precise rules, yet the source of this regularity is unexplained. Measurement confirms order without causal justification, leaving a paradox between observed lawfulness and its ultimate origin. You assume that the world behaves according to principles that are at least explainable, that the laws you observe have a cause rooted in physical necessity. Gravity acts consistently. Electromagnetism obeys Maxwell's equations, and quantum interactions follow probabilistic rules that are mathematically coherent. Observation validates this consistency across scales. Atoms form predictable structures, stars burn according to nuclear processes, and galaxies evolve according to general relativity. Measurement confirms the reliability of these laws, but offers no insight into why the laws exist in this form rather than another. Reality manifests order without revealing its origin. The paradox becomes apparent when you consider scale. Physical laws operate identically from the subatomic to the cosmological. The same mathematical structures describe particle interactions, chemical bonding, planetary motion, and galaxy formation. Observation confirms that the universe is not only orderly, but remarkably simple in its governing principles. The regularity is precise and measurable. Yet the source of this precision, why the equations governing motion, energy, and interaction take the forms they do, is entirely absent from observation. Measurement exposes the lawfulness of the universe, but the causal basis for that lawfulness remains undefined. This consistency also conflicts with expectations from contingency. You might assume that over vast space and time, slight variations would accumulate, introducing irregularities in physical laws. Yet observation shows uniformity. Experiments across laboratories on Earth, astronomical observations across billions of light years, and measurements of fundamental constants all confirm that the laws hold universally. Measurement validates coherence, revealing a structure that is finely tuned to operate identically everywhere. Reality exhibits regularity, so precise that it mirrors the predictability of a simulated system. Yet no underlying mechanism explains the origin of this uniformity. Even at the microscopic scale, the paradox persists. Quantum mechanics exhibits inherent uncertainty, yet statistical laws and symmetries are consistent and precise. Observation shows that fluctuations obey probabilistic rules that are mathematically exact, leading to emergent stability at larger scales. Measurement confirms both unpredictability and order simultaneously. The universe operates as though it were governed by a precise algorithm. Local randomness is constrained by overarching laws, producing global coherence. Reality enforces both flexibility and strict adherence to principles, measurable, yet without causal explanation. The paradox extends to cosmology and the evolution of the universe. Stars form, galaxies coalesce, and matter distributes in ways that obey simple, repeatable patterns. Observation confirms that these processes unfold predictably, yet the ultimate reason for such regularity is unknown. Measurement validates consistency, but the source of the laws ensuring it, why space-time behaves as it does, why forces obey symmetry, why constants take their values, remains entirely absent. Reality is lawful in observation, yet silent in causation. Ultimately, the simulation-like regularity exposes a tension between observation and explanation. You measure a universe that is coherent, predictable, and mathematically precise. Observation confirms patterns across scales, revealing consistency in the behavior of matter, energy, and space-time. Yet the source of these laws, the reason they take their particular form rather than another, is inaccessible. Measurement affirms order. Theory cannot fully account for origin. Reality is operationally intelligible, but conceptually opaque. Law-bound, yet causally enigmatic. Observation confirms regularity, leaving you confronted with the persistent and unresolved paradox of a universe that functions as though designed, while offering no explanation for the rules that make such functioning possible.